chair for the next session, which will contain 3 talks. So let us proceed immediately. And the first talk is by Valentine Leplat, who is currently a senior research scientist at Caltech. He is working on stochastic optimizations for the needs of training neural networks. So his portfolio contains engineering degree in mechanical engineering and in computer sciences and applied maths. He also worked for 6 years as an aerospace engineer. Soon after defending his PhD, he actually joined us in Caltech, and in between, he was also working as a postdoc under supervision of Professor Yuri Nesterov in Louvain, sorry for pronunciation, Institute. So I believe the floor is yours.
So can you hear me? I think you do. So hello everyone, I'm very happy to be here today in this seminar. So I will speak to you about some new stochastic optimizer that we call NACGS, which is, you will see semi-implicit, accelerated and robust. But first thing first, I would like to mention that the content of this talk is the result of nice collaboration with those gentlemen. First of all, Professor Ivan Ozoldet, then Daniel Merkulov, Alexander Katrutsa, and Daniel Bershadsky, who are a researcher at Caltech. On the bottom left of the slide, you have the reference to the preprint, which contains all the technical details of this subject, because today I will just give you some very, let's say, high-level ideas, the key ingredients that we use to build the stochastic optimizer. And the idea is to show what do you mean by robustness, why do you mean by acceleration, and by the way, robustness refers to the possibility of the optimizer to ensure high values for the learning rates, but also for the other parameters of the scheme. So first, some preliminaries. So basically, we would like to minimize some, by the way, I would like first to start with a pure deterministic point of view, then we will move to stochastic setting, but first deterministic. So we want to minimize some convex and strongly convex function with strongly convexity parameter mu and some Lipschitz continuous constant for the gradient. And for simplicity, the Hilbert space will be a finite dimension one, which is the most famous one, Rn. Okay, first I would like to Okay. Okay. Sorry, I'm not used to use such a things. I would like first to mention that the starting point will be the continuous time, and we will see that between some specific class of ordinary differential equation, which are referred to as gradient flow, there is a link between the way we solve ODE to solve such a things. Well, the simplest forward way is to use the Euler method. So it is a fully explicit method in the sense that if you want to compute the next iterate, well, you just need to have the information about the current iterate, and that's it. It's direct. But of course, this simplicity has some drawback, which is that this is not unconditionally astable. So it means that you have a limit, maximum limit on the step size or integration step, if you want to speak in terms of numerical analysis. There is a limitation on the maximum step size. In classical optimization, we usually consider for this class of function 1 over L, and you get some linear rate of convergence. By the way, for the strongly convex class of function with L-smoothness, the highest rate of convergence in terms of iterates has this form. It comes from Nesterov book, and in this formula you have QF, which refer to the conditioning number of the matrix, of the function that you consider. And another way to solve the Gledenflow ODE is to discretize with a fully implicit method. And this one is very nice because it is unconditionally astable, so it means that you can choose pretty much any kind of step size theoretically because you have some numerical limitation, but you can choose any kind of step size that you want and still get stability in the end, so conversions at the limit regime to the true solution of the ODE. Okay, we spoke about acceleration, and there are many ways in numerical optimization to get acceleration. Of course, you have the extrapolation and Nesterov style, but here the starting point will be the time continuous setting and with some spectral transformation of the original problem. And to show a little bit the intuition and the methodology, we will consider a very simple case, the minimization of a quadratic function where A is just a positive definite matrix. So if we write the gradient flow, this is what you have, but actually we won't tackle directly this problem, but we will change it a little bit. We will turn into a more general ODE system that you have on the bottom of the page with new variable with bigger dimension and a new matrix J. And what is this matrix? It is the first key ingredient. J is some asymmetric blocks matrix that actually will transform the spectrum of A from the real line because it's symmetric, a positive matrix, and you will transform it from the real line to the complex plane so that you will reduce the conditioning number in the end. So J, this conditioning number, is in the order of the square root of the original conditioning number of A. And thanks to that, actually, with some proper discretization method, you can ensure that you will get a much bigger step size. And actually, you will move from this linear contraction rate to this one, which is optimal for this class of function. So the idea is to have this transformation, this spectral transformation. What would be a good choice for this spectral transformation? In this talk, we will consider this one. As you can see, it's just some, well, it's a combination of the matrix A. And you have also some parameters. You have mu, which is the strongly convexity parameter of the function, but also gamma. And gamma is really important. It's positive scaling factors that actually follows its own ODE on the side. If we consider this transformation, and if we say, okay, Y is just a concatenation of X and V, so twice the dimension of the original gradient flow, and if we write the obtained system of ODE, we get this. And which is interesting is that, okay, let's imagine that you eliminate V from the system, and finally you will end up with this second order ODE, which is, by the way, something that has been shown 10 years ago by Boyd and Wisibono when they show that Nesterov acceleration actually can be derived in the continuous time in some kind of second order ODE. But here it's a little bit more general because of gamma. And gamma is really interesting because let's imagine that you have only a convex function, not a strongly convex function. Without gamma, you will lose these damping factors, which actually is the root cause for acceleration in optimization. But thanks to gamma, you will still get and ensure some damping factors and get acceleration. So gamma is really important. And by the way, for those who remember perfectly the seminal paper of Nesterov in 1984 on the first general scheme of optimal first order method, gamma is also present, but in a discretized form. So what is the goal of all of this? Well, we have seen acceleration, but we also seen that discretization strategy is central. And this is the second key ingredient today, is the way we want to discretize the ODE. In the best case, you would like to have something unconditionally astable. So it means that you can pretty choose any kind of step size that you want. But of course, there is some issues. And here an illustration, let's consider the general ODE system, so with this transformation J, and a fully discretization. The new iterate can be computed in this form with this formula, but it involves the inverse the computation of the inverse of some matrix. So it is unconditionally stable, but very costly in terms of computational effort. So we would like to have something in between, not explicit, not fully implicit, but somewhere in between, okay? This is why comes the term semi-implicitness. And how can we come with semi-implicit approach? Well, we have been motivated by, you probably know it, the Gauss-Seidel method that is used to approximate the inverse of a matrix. So basically what we will do, we will split the matrix J in two matrices, M, which is the lower triagonal part of J, including a diagonal, and N, the residual. And look, we will actually do an implicit discretization with respect to the terms, to the matrix M, and an explicit discretization for N. So we have some semi-implicit discretization thanks to this splitting. And by doing such a things, if you rewrite the new iterate, you will get this iteration equation. And because of the structure of M, this inverse can be computed very easily, in closed form actually, and in an analytical manner. So we have seen the key ingredient in the deterministic setting. Now it's time to move to the stochastic, which is the main interest of today. But stochastic in which sense? Well, let's imagine that, well, you have the notion of oracle in optimization method, and you want to ask, give me please the first order information at the current iterate. But the problem is that the oracle is getting a little bit old and it is not able to give you the actual gradient, but some approximation of the gradient. Basically, we can model it as the gradient plus some perturbation. For instance, in this case, the noise, which can be random. So the question is, yes, of course, you could, if you have a pure machine learning point of view, you could say, but okay, what is the link with machine learning world? Well, you know that when you minimize and train machine learning models, you do not compute the full gradients on the entire dataset. You compute some gradient onto mini-batch, randomly selected, and then you have some approximation of the full gradient. So there is also this notion of gradient plus noise. Does it change much? Yes, very deeply. And let's illustrate what would be the impact with noisy gradient on a very simple quadratic formula in one-dimensional case. So you have this quadratic form, and well, mu is the argmin of the function, obviously. And let's start with the gradient flow. Okay, those are the continuous time perspective, plus some noise. And the noise, we will model it, because we will at some point need to model the noise, the process. And well, in this case, we'll just consider some Brownian motion. And what happens if you want to solve this perturbated dynamics? Well, the trajectory x of t do not converge with the argmin with positive probability, but instead you will converge to some random variable, okay, which is centered around the argmin mu, but with some spreading characterized, featured by the variance that you have here. So it changed absolutely everything. So how can we integrate stochasticity in our spectral transform system of ODE? Well, we just add some noise to the gradient with a continuous martingale process, basically Brownian motion. And we end up with this system of stochastic differential equation now. The second thing is the discretization. Well, we will still apply this Gauss-Seidel splitting, this semi-implicit discretization, and come up with this actually discretized version of the system of SDE. And thanks to the Brownian motion, well, we can compute easily, of course, this term and the increment of the Brownian motion. And if you remember, you have the very important positive scalar factor gamma, which also satisfies some ODE, and we will also discretize its ODE in a fully implicit manner, because it's very easy to compute the update, even in fully implicitness approach. So you have a fully implicit discretization of the first SDE that you can easily compute. And you can solve and compute the next iterate easily, and then an explicit discretization of the second one. So basically the scheme, by the way, For those who already checked the paper and for those who will check later, you will see that the algorithm that is within the paper has been changed a little bit compared to this one because we just reformulate it in an equivalent manner just for, let's say, convenience of programmer. But this is basically the same thing. And if you also remember Nesterov acceleration method, then you can actually compare this method to the original Nesterov method, and you will see that basically it's very similar, except that Nesterov is actually considering some fully explicit discretization without knowing that. I don't know if you was aware of the time of the link with continuous time setting, but there is some nice relationship, and the difference is about the way you discretize the sequences. To choose the step size is a very complicated stuff, uh, especially in the stochastic setting. But actually, there are three manners, and we will just consider the most simple one, a constant step size. I don't have the time to go deeper in details, actually, but basically we analyze, we derive the maximum possible step size, ensuring the highest contraction rate. And how can we do such a things, ensuring stability of the method? And how do we do such a things? Well, basically we build the exact explicit formulation of the iteration matrix and the covariance matrix generated by the scheme at stationarity. And we compute the eigenvalues of those two quantities. And actually, this is how and we do that with respect to all the parameters of the scheme. And then we can analyze the stability, but it's very detailed, long, and technical, and to me, there is no point to present this in this talk. And let's move to some numerical tests. We perform. Okay, so we actually did a lot of numerical tests, and here I will just present one or two, showing that you can achieve really high rate, that you can ensure with this method a very large value for the learning rate. So here, simple logistic regression model, and we compare NACGS to Adam weight and SGD with momentum, and you have different kind of graph. And on each line, you have the train accuracy, the test accuracy, the train loss, and the test loss for different values. And if you, for different value of the learning rate. So the second row of graph is multiply by 10 the learning rate, and then by 5 for the top line. And as you can see, NACGS keeps very nice accuracy and a good trend for the lost evolution. But at some point, SGD, momentum, and Adam just break. So NACGS can give you ensure a very large value for the learning rate. Same thing for the transformers. So here it's Roberta in the glue benchmark dataset. And basically, well, the conclusion is the same. I will be very short. So you have 3 order of magnitude in terms of the learning rate that is ensured by NACGS. So basically, that's it for today. Thank you for the attention.
Thank you. Thank you. So do we have any questions? Okay, let me ask one then. So you were talking about matrices M and N for splitting in time this matrix or maybe function G. Have you thought of so-called prediction correction scheme where you have additional middle point k plus 1/2?
That kind of approach that you have, for instance, in the Runge-Kutta approach, when you have some, let's say, intermediate point. Yes, actually, this is a very good question. And I know that some people in the deterministic case, they consider prediction correction approach also and still manage to get optimal rate of convergence. So maybe that would be a good idea also to extend those prediction correction method to stochastic and see what happens. But we didn't explore it, but it's a very good point. Yeah.
Okay, thank you. Let us proceed to the next speaker, who is Jin Chen. She is a PhD student in Beijing Institute of Technology and Laboratory of Intelligent Information Technology. She's working under supervision of Professor Xinxiao, sorry for wrong pronunciation, Xinxiao Wu. And she also got her bachelor degree also in the Beijing Institute of Technology. Her current research interests are domain adaptation, causal inference, and knowledge reasoning. So, please.
Thank you for your introduction. Oh, hello everyone. I'm glad here to share our paper Adaptive Image to Video Scene Graph Generation with Knowledge Reasoning and Adversarial Learning. This work was done in Beijing Institute of Technology and published at AAAI 2000 and 2022. And I thank our co-authors Xiaofeng Ji, Professor Xinxiao Wu. For scene graph generation in videos, it is a time-consuming and labor-intensive process to annotate large-scale training videos with objects and relationships in each frame. On the other hand, it is much easier and less cost to annotate images with scene graphs. So we investigate leveraging annotated images to facilitate training a scene graph generation model for unannotated videos, namely image-to-video scene graph generation. This task presents two challenges. First, due to the absence of motion information in images, it is necessary to infer unseen dynamic relationships in videos from stick relationships in images. Second, there exists the domain shifts between image and video domains, and the objects and the stick relationships should be adapted from images to video frames. For the first challenge, our insight is that a dynamic relationship can be inferred from the temporal evolution of related stick relationships as illustrated in Figure 1. The dynamic relationship person right past person can be inferred from sequential stick relationships between person and person, right front, right left, and right behind. We denote such association between stick and the dynamic relationships as common sense knowledge, which can be explored from many external text resources such as Action Genome and Wikipedia. For the second challenge, there is a two-level domain shift. As shown in figures, the image level domain shift is caused by the variance of image style and elimination. The instance level domain shift is caused by the variance of object appearance and size. To address the first challenge, we propose knowledge reasoning to infer unseen dynamic relationships in videos. We first construct a relationship common sense base to model the association between stick and dynamic relationships. With the guidance of common sense knowledge, we then learn to generate the embedded feature of an unseen dynamic relationship from its associated sequential stick relationships in the vision language embedding space for prediction. To track the second challenge, we propose hierarchical adversarial learning to reduce the domain shift in both image and instance levels for adapting an object detection model from images to video frames. Specifically, the image level shift is minimized by arranging the second order statistics of the image and video frame features. The instance level shift is minimized by arranging the distribution of region proposals of image and video frames. In this way, we learn the domain environment visual object features of image and video frames, thus benefiting the prediction of stick relationships in video frames. Hence, our contribution is summarized as the following. We propose a new task, image-to-video scene graph generation, that adapts well the scene graph generation model trains using annotated images to unannotated videos. This task breaks the heavy dependence on large-scale videos, annotated with objects and their relationships for training, making it more practical and general in real-world scenarios. We propose a knowledge reasoning method that explores external common sense knowledge to infer ancient dynamic stick relationships from the temporal evolution of stick relationships. We propose a hierarchical adversarial learning method to reduce the domain shift between image and video domains for promoting the adaptation of objects and stick relationships. Next, I will introduce our method in detail. Our method consists of three models: a cross-domain object detection model, a stick relation prediction model, and a dynamic relationship learning model. The cross-domain object detection model learns domain environment features between images and video frames by hierarchical adversarial learning to reduce the image level and the instance level shifts simultaneously. The stick relationship prediction model learns to project both the domain environment visual features and the language feature of each relationship into a visual language embedding space to generate visual embedding and the language embedding respectively. The dynamic relationship learning model learns to generate the visual embedding of dynamic relationships from sequential stick relationships by exploiting the external relationship common sense space. In this task, we are given an annotated source image domain and an annotated text video domain. The source domain is denoted as DS, where XIS represents the S image, and the GIS denotes the scene graph generation of XIS. The text domain is denoted as DT, where XIT represents the S video. Each video consists of multiple video frames, and the G frame of the S video is represented as FIG. To address the image level shift and the instance level shift between image and the video frames, we propose hierarchical adversarial learning, including image level adversarial learning and the instance level adversarial learning. As shown in this figure, the image level adversarial learning is performed at low-level features since these features contain more textual information. Hence, we split the whole feature extractor F into F1 and F2 and construct an adversarial component on F1. The instance level adversarial learning is performed at instance features. For image level adversarial learning, we align the second order statistics of the image and video frame features to reduce the image level shift, since the second order statistics contain pairwise correlations between features, while reflecting the detailed information in images. The second order statistics of image feature and video frame feature are computed by factorized bilinear pooling scheme, denoted as GIS and GIGT respectively. An image level domain classifier DImage learns to distinguish the second order statistics of image from that of video frames, formulated as this equation. The feature extractor F1 tries to confuse the image to make the second order statistics of the two different domains as indistinguishable as possible. The image at F1 are trained in adversarial manner by a gradient reverse layer. For the instance level adversarial learning, we introduce an instance domain classifier DINS to predict multiple domain labels for pixels of a region proposal of image or video frames, formulated as this equation. Including a visual mapping file and a language mapping set. We use image and their corresponding scene graph scene graph annotations to learn the vision language embedding space. Given a relationship, the visual feature Z is extracted from image consisting of domain environment visual features of subject, object, and predicts, and a special feature of the relative location of stick and object. The language feature E is represented by an word vector of the predict label. We project Z and E by the two mappings formulated as this equation and obtain the visual and language embeddings of this relationship. Then we optimize the visual language embedding space by minimizing the distance of the matched visual and language embeddings and maximizing that of the mismatched bands. To learn dynamic relationships, we construct a relationship common sense based about the association between a dynamic relationship and a sequential of stick relationships. Afterwards, we propose knowledge reasoning to first generate an associated sequential stick relationship for a dynamic relationship with the guidance of common sense knowledge, and then learn a visual embedding of the dynamic relationship from the generated sequence by minimizing its distance to the language embedding. The relationship common sense base is constructed from both the popular action recognition dataset, action genome, and the most widely used visual relation detection datasets, the VID dataset and the VID-OR dataset. In action genome, each action corresponding to 5 temporal sequential scene graphs. The action is actually a dynamic relationship, and the stick relationships with the same subject and object to this action are chosen from the 5 scene graphs as a sequence of stick relationships associated with the dynamic relationship. For the VID dataset and the VID-OR dataset, we first count the frequency of stick relationships that appear together with the dynamic relationship of the same subject and object, and then summary a rule manually according to the frequency. Totally, we obtained 2,049 rules about 35 dynamic relationships and 36 stick relationships to build this relationship common sense base. Based on the common sense knowledge, we propose knowledge reasoning to learn dynamic relationships. For a dynamic relationship RA, we retrieval its corresponding rule in relationship common sense base. With the retrieval rule, we obtain domain environment features of these stick relationships by sampling predicted relationship instance of video frames and obtain visual embedding. Then the visual embedding of RA is generated by aggregating visual embeddings of sequential stick relationships via LSTM. The language embedding WA is obtained via language mapping cassette. Finally, the distance between visual embedding ZA and the language embedding WA is minimized to optimize LSTM, formulated as this equation. We conduct experiments on 2 video benchmarks, the VID dataset and the VID-OR dataset. With the VID dataset as the target domain, we use the VRD dataset as the source domain. With the VID-OR dataset as the target domain, we use the VD dataset as the source domain. For the 2 tasks, we use the objects and their relationships shared by the source and target domains to train and evaluate. The dynamic relationships that only exist in the video domain. We adopt the unsupervised domain adaptation protocol, where the training data consists of unannotated images from the source domain and unannotated videos from the text domain. The annotation of text videos are only used for evaluation. To the best of our knowledge, this is the first work for the new task of image-to-video scene graph generation. So the most related methods to our method are the methods of video scene graph generation that use annotated videos for training. We implement the method of VID using our training data on the VID dataset for comparison. We also compare our method with several variants to demonstrate the effects of each component. Since both the relationship detection task and the relationship tagging task are based on the object detection results, we use the ground truth of the object detection as the object detection results to evaluate the relationship task deeper, denoted as oracle in the bottom of this table. Due to the time limitation, I have shown the results on the VID dataset. In comparison with the VID methods, our method performs worse on stick relationships due to the unavailable annotation of videos, but achieves better performance on dynamic relationships. This promising result shows that it is beneficial to exploit external knowledge for inferring dynamic relationships from sequential stick relationships. When removing the knowledge reasoning, our method fails to predict dynamic relationships. Oracle achieves better results than supervised video scene graph generation method, showing the feasibility of learning a relationship prediction model from existing annotated images with given good object data, and the significance of learning a better cross-domain object detection model. To further analyze the effectiveness of hierarchical adversarial learning model on reducing the domain shift, we visualize the object features of images and video frames learned by without adversarial learning, without image level adversarial, without instance level adversarial, and others using TSNE in this figure. We also show the Sesssion diverse of source and target data distributions. The larger the Sesssion diverse is, the more different the data distribution are. In figure 3a, the data distributions of different domains are quite different. We illustrate our quantitative results in figure 4. Our method detects stick relationships of stand right, work left, and stand next to and feed well. By the knowledge reasoning model, our method succeeds in inferring the dynamic relationship of work toward, guided by the rule that the dynamic relationship work toward can be inferred from sequential stick relationships work left and stand next. In other words, the LSTM learns the visual embeddings of dynamic relationships successfully while transferring common sense in relationship common sense space to the visual language embedding space, further demonstrating the effectiveness of the knowledge reasoning. Okay, let's take a summary. We have present a new task called image-to-video scene graph generation that leverage annotated images to train a scene graph generation model for videos. This task breaks the heavy dependence on large-scale annotated training videos, making it more approaching to real-world application. To infer dynamic relationships in videos, we have proposed a knowledge reasoning method that can generate visual embedding representations of unseen dynamic relationships for prediction while exploiting common sense knowledge. To reduce the domain shift between images and videos, we have proposed a hierarchical adversarial learning method that can learn domain environment visual features to enable the adaptation of objects and stick relationships from images to video frames. Extensive experiments on the benchmark datasets have validated the effectiveness of our methods. That's all. Thanks for your listening. Here is the link of our code. Next time is for question and answer. It's my pleasure to have a deeper discussion with everyone. Thank you.
Thank you. Let me say thank you for your talk. So we have only time for one short question, if there is such.
Okay. Okay, thank you for your presentation. You proposed a new interesting task. The proposed methodology seems overall reasonable. I just wondered whether there is a intuitive and simple one. If the first method is so complex, the following works may fall into a limited track. Oh, thank you.
Oh, thank you. I have understand your question. This new task is challenging due to the two issues, the absence of temporal motion information in images and the domain shift between image and video frame. It's necessary to infer unseen dynamic relationships from the temporal evolution of stick relationships by using the common sense knowledge of association between stick and dynamic relationships. To address the second issue, it is also intuitive to learn domain environment features of image and video frames via adversarial learning. In my opinion, following works can design different methods to handle these issues. That's all.
Okay, thank you.
Thank you. Let us shift to our last speaker for this session, and the speaker is Gonzalo Ferrer, who is an associate professor at Caltech, where he is heading mobile robotics lab. He completed his PhD thesis on robot navigation algorithms in urban environments at the Institut de Robótica Informática Industrial, which is a group inside University of Polytechnic Catalonia in Barcelona. After that, he did his PhD studies and was intermittent lecturer in the University of Michigan. So, please.
Yes, I'm ready. Sorry, I was just... Okay, thanks for the introduction. Closer. Okay. Okay, I guess we have image from this. Okay, so I'm gonna talk about vision plane SLAM. This is also a little bit introduction about my group, right? So we are the Mobile Robotics Lab. So far, we have been here for some time at Skoltech. We have some researchers, PhDs, masters. What will be our objective, right? So we want to deploy robots in urban environments, indoors, and just navigate intelligently. The problem with this is that the world is very complicated. You need to do a lot of research on perception, right? So how to understand the world. And then there's a second part that is equally challenging, which is about action, right? How to actuate, succeed in the world, and these kind of things. Okay, so today's talk is mostly going to be on perception, but it doesn't mean that we don't care about navigation and planning. Okay, so this is the start. This is the motivation of the talk. We have sets of point clouds that could be either obtained from RGBD cameras or from LiDAR. At the end, these point clouds are very rich, right? So they give you very precise depth estimation. So you have with few error, how far away things are, let's say, in a scene. But the problem is that it's very hard to know exactly what point corresponds to what point, right? So we see the counterpart in image-based. So here, this is the result of a structure from motion. This is an example that you have when you take a bunch of pictures and you just apply this algorithm in this case, right? So you have a set of sparse key points and you align all your camera poses with this. So this part, what is interesting about this is that you don't use the full images, okay? So you could do like dense reconstruction, yes, there's approaches on this, but let's say that this is very efficient because you are using only few key points in the scene, like corners, parts of the windows, etc. Right, and the question that we were asking is, can we do the same thing for point clouds? So we don't have this texture that gives like this description, right, that allows this easy data association. Let's say that this is another problem, but so far how point clouds are used are still not, let's say, on par of the computer vision part with images, right? So we want to define like what are these basic elements, these points that are in images, what are these basic elements that will allow to have like SLAM with point clouds equally as bundle adjustment here with images, okay? So for this, I'm just gonna go a little bit back and you will see like why is the motivation on doing this. So we are just going to start discussing about plane estimation. Okay, so a plane is just a flat surface in the 3D space. Here, what we have is a point, and we say that this point belongs to this plane pi if this constraint is satisfied. Okay, so this is just like the definition. Now, what will happen is that you have a bunch of points that are observed, let's say, with a sensor, and this sensor has noise. And you don't know the plane parameters, right? So the question is not really like if the point is on the plane or not, because this is just the definition. But if you have a bunch of points, how can you estimate the plane parameters, right? Okay, so there's two main methods. So the first one is what we call the center plane estimation. This requires to have like the expectation of all these points equal to 0, right? So at the end, you are saying all your constraints should match more or less, okay? So there's gonna be, well, some error, but we'll see later. Okay, so from this definition, we just go to all these points. Every time that I'm writing here P of n, this means that observed points from a sensor. And if you rearrange things a little bit and remove the mean, what we get is this very, well, here, basically what we have is what is called also point-to-plane error. So at this point, this is gonna be interesting because it's not just for plane estimation, but we will see later that we can use this for SLAM. So what we get is this compact expression here, okay? So all these points rearranged in this form, and this is some sort of, well, this is actually a covariance matrix. This is the solution of the problem, right? So with this, you just apply the eigen decomposition, get the normal, and then you can calculate distance. Okay, there's a second way of solving the problem, which is the homogeneous approach, which is very similar, but we are just redefining the constraint on homogeneous coordinates. Okay, so now this is a little bit more compact. We have like this constraint, and the idea is the same. Okay, so here I'm not creating the summation, but instead we have just stack matrix of all the homogeneous points. And the interesting thing is that if you just do this, let's say, inner product of matrices, you end up having a 4x4 matrix, right? So this matrix we are calling S, and the solution of the plane again is going to be the eigen decomposition, but now from a 4x4 matrix. We are going to get the plane coordinates, and you just need to scale, right? To scale them if you want to have them in proper values. Okay, so now comes a little bit the SLAM part. So SLAM here, what we want to estimate is, let's say, the camera poses, all these points all these poses in the space from where all the points were taking, right? So this is the trajectory that, let's say, a robot or someone with a camera or a sensor moving or flying drone, doesn't matter. They are just taking from some different reference frame, okay? And the assumption here is going to be that we are observing the same plane. So you can observe the same plane from a reference frame, that is this one. But also, if you move, you are going to be observing the same geometric entity, right? So the only thing we are doing here is transforming points. These points here are in the local coordinate frame of each of these observations. And you just need to transform this to some other global coordinate. Okay, so we can do this for all observations, and this is going to be how we define like this error. Remember that estimation of points is just minimizing point-to-plane error. But with this, what we want to optimize is the camera poses, right? All these poses in 3D that are telling us like what is the trajectory that we have followed. Okay, so so that's how, I mean, this is kind of a little bit the motivation, but now let's get into what we were proposing to do. So we call this technique the eigenfactors because, well, we'll see that later there's eigendecomposition. But one of the first properties that we can see from this summation of all points is that, in fact, all these point-to-plane errors can be expressed just with a simple 4x4 matrix. Okay, so here what we see is that for estimating this plane, this gets away from the summation, and we have like this summation of all these matrices. If you see this, this is the S matrix that I was talking before. This is just compression of points. And the great thing about this is that you need just to calculate these ones. Okay, so why is this important? Because every time that you're estimating your solution, you can do like point-to-plane error with all points, and you just need to estimate, you just need to calculate them once. And once this S matrix is calculated, the number of points is not affecting the complexity, right? So this is a great feature. If you have a method that is independent on the number of points, you could be using here like millions. And the only thing you want to do is just find like the same planar surfaces. The other interesting thing is that for this to work right is that all these 4x4 matrices of homogeneous outer product summations are in the local frame, but you can transform them very easily, right? And this is the form here. So we see that this transformation here is not just applying, I mean, it's basically transforming this matrix from both sides, right? At the end, the result is the same as if you had like points transforming your residual. So this is a great property because it's telling us you don't need to recalculate things. You just calculate them once in your local frame, and then if you want to use them in other frames, you just transform. Okay, and the other interesting thing is that you can sum all of them. Why is this possible? Why you can sum all these, let's say, cluster of points or these aggregated points? Because they are on the same reference frame. Okay, so all this is just transforming them to the world. Okay, so then at the end we just compose like this matrix, and this is it, right? So this is just, we have here all poses, all of them from time, well here, yeah, this is a little bit not correct, but from time 1 to all the time horizon, and we just need to solve the problem that we described before, right? Now, the problem is going to be a little bit different because what we have is that this Q function is actually a function of all the previous poses, right? But the interesting thing is that we discussed before that if you just do plane estimation, there's a closed form that is just consisting of just calculating what is the minimum eigenvalue. Okay, so we have this, we remove one minimization, which is great. And this also has some other consequences that I'm going to discuss later. And if we have our plane, it's just going to be proportional to this minimum vector. Okay, so now once we have calculated this, it's we need to redefine things slightly because what we want to do is actually optimize over this value. Remember, this value is similar to the point-to-plane error. So it's accumulating all the errors on all points. But what we want to do is not to estimate the plane. This is just a mean. This is just a connection of all the observations. What we want to do is estimate poses. Okay, so this is always the end objective. So for this, what we need to do is just minimize this. So we want this minimum eigenvalue to be smaller, as small as possible. Ideally, it should be 0. Yes, if you have perfect observations of your planes. It will not be because reality is very stubborn by even with very expensive sensors, but still this is the objective. Okay, so for this we need to define retraction because later what we want to do is derive gradients and Hessians over this expression. But as it is now, we cannot really do it. So we define just a retraction. Here we have rigid body transformations. We have chosen this, in this case, just the exponent map. We could have chosen any other retraction, but it's very convenient because this will allow later to calculate derivatives very easily. Okay, so, but here, I mean, let's say the only important thing is that we need this kind of function. Okay, and then later we just do function composition of all the other elements. Here for the matrix Q, kind of happens the same. I'm here just writing for one element, but you need to imagine that for all elements for each pose, let's say that this is going to be a summation. And then the final composition is this, right? So we are going to have just this lambda function, which we can obtain. And it's just going to be the composition of Q matrix and then retraction, right? And the great thing about this is that for one pose, this is going to be times n, right, for the number of poses. But for one pose, we get just from these increments of what was our current pose, I mean, yes, to just a value that is our error, right? So with this, we can define directional derivatives, and we are ready to define like optimization. Okay, so how can we calculate like gradients over the eigen decomposition? Well, there's a constraint on the values. These vectors, remember that these are our planes. And thanks to this constraint, we will not need to calculate gradients, or we don't need the parameters of the plane at all, right? So this is very important because at the end, estimating the plane is not necessary. It's not required. The only thing we need to do is just calculate derivatives, and this is the derivative with respect to the minimum eigenvalue. We just need to multiply like this matrix. Well, now the derivative of this matrix, so we'll see that this is a little bit an issue, but the important thing is that although it started being a definition of how can we estimate a plane, to calculate poses, we don't really need this. So we don't need the intermediate landmarks that we were saying. They are going to be there. You need to calculate them, of course, but just to minimize the, let's say, alignment of all poses, we don't need to calculate like gradients over this, okay? So with this, well, basically we obtain like some gradients, some Hessian, and I'm just showing here an example of this point cloud alignment. So this is a synthetic environment. We started with, let's say, some pose. And then at the end, from all these poses, we're observing these points, right? So this is, let's say, the initial condition. We started with some noise, and we see that after optimizing over the Fs, we see planes that are like really matching, right? So this is good because it's not just that we are showing like crisp images, but it means that the trajectory error has been improved, right? So this is what you want, to have better trajectory. Okay, just few comparisons. I didn't talk too much about ICP, but ICP is a very famous method just to kind of calculate transformations between pairs of points. Here, it's a little bit different approach because what we are saying is, let's not just calculate alignment between two poses, but with n poses, right? So what we see is that if you just have two poses, both ICP and ICP point to plane are kind of superior. But if you increase the number of poses that you're observing, and here we are just comparing first and last pose for ICP, that's why this thing is flat, then it really brings an advantage to use more poses, to use, let's say, these intermediate eigenfactors as we were defining. The other interesting takeaway from here is that previous techniques, let's say on landmark-based SLAM, what they were doing is estimating the plane at each observation. Okay, so let's say you have RGBD, you have LiDAR, you extract plane, and then what you add into the system is just the plane estimation at this current observation. Okay, and we see that this is not a good idea. So this is here like landmark-based SLAM, if you want, of planes obtained. So what we see is that depending on the noise that you have on the observations, this estimation is going to be noisy. So at the end, you are just going to fit a lot of observations of planes, multiple of them for each observation. Remember that there's no way of putting everything together. I mean, on this definition, it just goes plane by plane. So this at the end requires like all these landmarks that you're assuming that don't have biases and other problems, which at the end they do, they have. And what we see here is that, okay, so this is gradient-based AF, so this is not good. But if we apply second order methods like Newton here or Levenberg-Marquardt, the results we are getting are much better, okay? And we see the same thing here for the landmark base, right? So this is the error with respect to the number of points on each plane. So of course, if you have infinite points, this landmark-based approach is going to be good. You estimate based on your observations. But the point is that LiDAR is not uniformly, I mean, the points are not uniformly distributed. You have gaps. Density is not regular as well. So you cannot really rely that you are going to have very accurate planes every time that you observe them, right? You need to accumulate them. Okay, what comes next? So we really want to benchmark this on LiDAR and RGBD benchmarks. So this is some examples of some of the benchmarks we are considering here: Kitty, ICL, TUM, very famous sets. We need to work here also on the front end, plane detection. So we have also been working on this, but let's say that this is for another talk. What are the remarks that I want just to highlight, just to finish, right? So we have discussed a backend SLAM that is more efficient. Why it's more efficient? Because you don't need to estimate at all. First of all, you don't need to process points every time that you are optimizing, which is a great feature. So number of points is not important at all. You just calculate this S matrix once and you are finished. And the second improvement on efficiency is that you don't need to estimate landmarks. So you need to imagine that each plane is 4 dimensions. So your state vector is now reduced. You only calculate poses, if there's like poses. So you are just reducing the dimensionality of your problem, right? So this was not there on, let's say, classical landmark plane SLAM. But with this, you don't need to calculate it because it's already there. It's implicit on when you calculate the eigenfactor. So front end is equally important. So front end is plane extraction, outlier rejection, association. All these things are still very important. I didn't talk about this here, but this is something that you need. And also a very, very interesting thing is like sensor fusion, right? So visual data is very rich. You have a lot of texture, but you don't have this depth estimation. And depth on the other side is like very accurate, but you have gaps. You have like observations that, I mean, part of this scene is not observed every time. Okay, so this basically is kind of, let's say, interesting topics that we're still working on, kind of future trends, possible collaborations. But this combination of front end and back end, I think this is also like a research line, how to improve robustness, how to one help the other, and so on. Okay, so thanks for the attention, and you can contact me here, and I'll be happy to answer questions.
Thank you for the talk. So we have one time for one short question. Okay, let me ask it then. How do you split your points into some clusters for initial planes?
Yes.
When you already have this separation, applying eigenvalue decomposition is simple task, but the hard task is to combine these points together. How do you combine them?
Yes, yes. So you are talking about labeling these points as belonging to the same plane. So this is the challenge that I was saying here. So this is part of the front end. Here, what you can do is you can apply robust filtering if you want to reject part of the planes, let's say that they are incorrectly labeled. And of course, you need a very good plane detector. So this is part of the problem. It's not that it's easy once you have planes, because as I said, the classical approaches were just estimating planes and then optimizing, and with this you have more error. With this, yes, this is part of the problem. But let's say that didn't answer this question in this talk. But I acknowledge that yes, this is like something you need to work on. But it's not that it's impossible. I mean, plane detectors these days are very good. So you can imagine them as simpler versions of semantic segmentation. So you can take networks and just reduce them a lot, and with this, the output is still good.
Okay, thank you. So let me finish this session. Let us meet in 2 hours after lunch break. Or dinner break, yes, indeed. Thank you for coming. Thank you for attending. See you.
中俄战略合作以及区域经济。
Okay, thank you for the speakers and the very impressive talks. Okay, after lunch break, the session will start at 1:30 p.m. in Moscow time and 6:30 p.m. in Beijing time. Okay, see you later.